All right, let's consider making measurements. Pretty much everything we have to do in chemistry is going to be done in the lab. And if we're going to do stuff in the lab, we are going to have to make measurements. Now, each measurement provides three types of information. It provides a size or magnitude of the measurement, which is the number. It provides a standard of comparison for it, which is the unit. And then we also have an indication of how well we know the measurement, or the uncertainty, which is going to be in the number of significant figures, or sig figs as we call them for short. So number, unit, and then how well we know the measurement. A measurement without a unit is pretty much meaningless. So, for example, if I just told you you had 15 of something, you'd go 15 what? Is it 15 cups? Is it 15 pounds? We have to have a number, and we have to have ourselves a unit. We're going to use a couple of different systems in this. We're going to use the metric system, and we're going to use parts of the SI system when we do our measurements in chemistry. So before we go into that, we need to make sure that we are well versed on scientific notation. Scientific notation is just how we deal with very large and very small numbers. For example, there are that number of atoms in 12 grams of carbon-12. Or if we wanted to look at the diameter of a carbon atom in meters, we'd have this one. Now, we don't really want to have to write these, so we are going to take and we are going to instead put these into scientific notation. We're going to get rid of the zeros. So this one number looks like this, and this number looks like that. So let's make sure we remember how to do this. In scientific notation, the standard way of doing this is that we have a coefficient, which is a number between 1 and 10, and then we have a positive or negative integer that our 10 value is raised to. So for the example, if we had 100, 100 is the same as 10 times 10, that's 2 tens, and we'd call that 10 squared. If we have 1 over 100, we have 1 over 10 squared, and we write this as 10 to the minus 2, giving a positive exponent for a large number and a negative exponent for a small number. So if we have 150 meters, it is going to be the coefficient 1.5 multiplied by 100, which is 10 squared. If we have 0.0075 liters, we're going to have 7.5. This is going to be divided by 1,000, and so we're going to have 7.5 times 10 to the minus 3 liters. We can also take and shift our decimal to do this, which is how we tend to do these. So what we want is we want the decimal to be behind the first non-zero digit. So if we have 52000, now the first thing you're going to do is we're going to put the decimal in. Each time we move the decimal, we're going to move it by a factor of 10 or a power of 10, and we're going to go 1, 2, 3, 4, and we move it 4. This is a large number. If we move it left, our exponent is positive, and we're going to have 5.2 times 10 to the fourth. If we take and we're going to do a negative or a smaller number, we're going to move this 3 spaces to the right, again, decimal behind the first non-zero digit, and we're going to have 3.78 times 10. Moving it to the right gives us a negative. Number of spots is going to be 3. So if we took and we converted these guys into scientific notation, this is a small number. We're moving the decimal to the right, and we're going to have 5.43 times 10 to the minus 4 grams. Here we're going to move the decimal to the left, 1, 2, 3, 4, 5, 1.024 times 10 to the fifth meters. Here, 1, 2, 3, 4, 5, 6, 7, 5.65 times 10 to the minus 7 seconds. We could also take and put numbers in scientific notation into standard numbers. So if we're going to do 10 to the minus 4, we're going to have 2.3, and then we can put our zeros in. We know we're going to move it 4 spots, so 1, 2, 3, 4, and that is going to be our answer. 0.00023 is the same as 2.3 times 10 to the minus 4. If I have 6.4 times 10 to the third, again, I'm going to put zeros in. I'm going to move it 3 places, 1, 2, 3, and that's going to give me 6,400. Putting in our units. All right, so again, when we make our measurements, we're going to have a number in front, we're going to have a unit telling us our comparison point, and then how well we know it. So looking at some of the base units that we're going to use in this class. If we're going to do length, we're going to do the unit of meters. If we're going to do mass, using the metric system rather than the SI, we're going to use the unit of grams. We just don't measure kilograms. In the lab, it's too big. Time is seconds. How much we have of a substance is going to be moles, and we shorthand that with an MOL. But the most important units that we have here are length is meters, mass is grams, how much is moles, and then temperature. We're going to have two different units we use for temperature in this class. We're going to have the SI unit, which is kelvins. We use the SI unit because 0 kelvins or 0 K is absolute zero, which means there's no heat remaining, meaning you can't get it any colder, as compared to the other unit that we use in the class or in the lab, which is going to be in degrees Celsius, which is a degree C. Note there's no degree sign here on kelvins. With degrees Celsius, 0 degrees Celsius is a temperature where water freezes, which really has nothing to do with being zero. Zero should be nothing left, which is why absolute zero makes perfectly good sense. And the temperature scale in Celsius is a little mediocre. Now, instead of the English system where we go from small to big by changing units like teaspoons to tablespoons to cups to pints, etc., in the metric or the SI system, we go from smaller to bigger using prefixes. A prefix means in front. So, for example, one you might be familiar with is a kilo. A kilo is symbolized by a lowercase k, and it means 1,000. We can put a kilo in front of any of the base units. So, for example, we can have a kilometer, a kilometer. So let's just call it a kilo or kilometer here. And so a kilometer is going to be the same here as a k, lowercase m for kilometer, which is going to be the same as, since a kilometer is 1,000, is 1,000 meters. And these are all interchangeable. And the kilo could also go in front of grams. So a kilogram or kilogram is going to be a kg, which is going to be 1,000 grams. It's a prefix. It goes in front of the units. This is a list of them. I'll give you the list that you need to memorize in a couple of slides. Some relative lengths. A meter is about a yard. There are, in fact, 39.36 inches in 1 meter, which is going to be a little bit over a yard. Other things we use is that we can look at centimeters, and we compare centimeters to inches. There are exactly 2.54 centimeters in an inch. I need you to be able to convert inside the metric system, but not in between the English and the metric system. If I need you to do those conversions, I will give them to you on the test. All right, metrics prefix system. These are the ones I need you to memorize. I need you to realize that a kilo, which is a lowercase k, means 1,000. So if you have 1 kilogram, you're going to have 1,000 grams. In your head, probably put mega as well. A mega is a capital M, and it's a million, 10 to the 6th. The rest of these are all for smaller, and we tend to use smaller in chemistry rather than larger. So, for example, a deci, and these are prefixes. Now, we're going to have two ways of looking at these, and you're going to have to sort out how you can learn them. A deci is a 0.1, and we can consider here that if we have 0.1, that's the same as 1 over 10. So we can either memorize that a deci, lowercase d, is 0.1, or we can memorize that there are 10 deci in something. This is set up, so we're doing it the second way. And so look through these. We want to do a conversion. There are 10 decis in 1. There are 100 millis, or 100 centas in 1. 1,000 millis in 1, 1 million micros in 1, and 1 trillion nanos in 1. So this is an option on memorizing them. You can also go back to the previous slide and learn the other way that that a centa, for example, is 10 to the minus 2, and that a centimeter is 10 to the minus 2 meters. A lot of people have an easier time with these and simply memorize that there are 100 centimeters in a meter. So the best way to do that is to simply practice it. So if we consider centas, and we know that there are 100 centa in something, if we have centiseconds, it tells us that there are 100 centiseconds in a second. So if we have 1 second, we have 100 centiseconds. Now, if we're looking at a million, we know that there are 1 million micros in anything. So if I have 1 gram, it is the same as 1 million micrograms. Now, 1 liter. If I want to do my conversions between liters and something smaller, my classic is going to be a milliliter. A milli, by the way, again, there's 2 ways of doing all of these. A milli is 10 to the minus 3 or 1 over 1,000. So we can either say that there is or there are 1 over 1,000 liters in a milliliter, again, because that is equivalent to a milli, or we can multiply through and say that 1 liter is 1,000 milliliters. Well, if 1 liter is 1,000 milliliters, then this is 1,000 milliliters. Here is 1 liter. Now, this is the opposite one. And if we have 1,000 meters, we know that this is 1,000 is the same as a kilo. And so this is going to be 1 kilometer. And now, because we're scientists and we're bored and we're scary, let's play with these two. Milli. There are 1,000 milli in 1, which is the same as 100 centa equally in 1, because these cancel themselves out, which tells us that there are 10 millis in 1 centa. So if we have 10 millipedes, we are going to have 1 centipede. Yes, that's supposed to be a joke. If we have 2,000 mockingbirds, well, we know that if we've got 2 times 10 to the third, 10 to the third is the same as a kilo, so this is going to be 2 kilo mockingbirds, or To Kill a Mockingbird. I know, sorry. All right, let's make sure we're comfortable on some derived units, meaning based on other units, other smaller or base units. So volume. Volume in chemistry is going to be the unit of a liter. Meter cubed is what it's do in physics, and that's just way too big for us. So 1 liter is the same as 1 decimeter cubed. A deci is 0.1. So if I take a volume, by the way, volume is length times width times height of 0.1 meters times 0.1 meters times 0.1 meters, I will get 1 decimeter cubed, which is going to equal a liter. Now, there are 10 centimeters in a decimeter, and so I can equally take a look and do this in terms of other units aside from just a liter. So 1 decimeter cubed is a liter, which is going to be the same as 1,000 centimeters cubed, which is going to be the same as 1,000 milliliters, or equally 1 centimeter cubed is equal to 1 milliliter. You need to know these as they are used interchangeably in chemistry. So once again, there are 1 centimeter cubed in 1 milliliter. If you're in the medical field, you might actually call this a cc for a cubic centimeter. And We know that there are 1,000 milli in anything, so there's 1,000 milliliters in a liter, which is the same as 1,000 cubic centimeters. The last unit or set of derived units we need to consider is the units for density. Density is mass over volume. One cute way to do this is to take and do density as m over v, mass over volume, and it's just going to be how much something weighs, which is going to be in units of grams. If it's a liquid or a solid, we tend to do it in grams per cubic centimeter or grams per liter or grams per milliliter, because remember these two are identical. For a gas, we do units instead of grams per liter because the density of gases is so low.